Thermodynamics, state variable and equation of state. Every equilibrium state of a thermodynamic system is completely described by specific value of some macroscopic variables, also called state variables. For example, an equilibrium state of a gas is completely specified by the value of pressure, volume, temperature, and mass. A thermodynamic state is not always in equilibrium. For example, a gas allowed to expand freely against vacuum is not equilibrium state. During the rapid expansion, pressure of gas may not be uniform throughout. Similarly, a mixture of gas undergoing an explosive chemical reaction is not an equilibrium state. Again, its temperature and pressure are not uniform. Eventually, the gas attain a uniform temperature and pressure and come to thermal and mechanical equilibrium with its surrounding. The partition of the box is suddenly removed, leading to the free expansion of the gas. A mixture of gas undergoing an explosive chemical reaction. In both situations, the gas is not in equilibrium and cannot be described as state variables. In short, thermodynamic state variables describe equilibrium state of systems. The various state variables are not necessarily independent. The connection between the state variable is called equation of state. The connection between the state variable is called equation of state. For example, for an ideal gas, the equation of state is the ideal gas relation, that is PV is equal to mu RT. For a fixed amount of gas given mu, there are thus only two independent variables, say P and V or T and V. The pressure volume curve for a fixed temperature is called isotherm. Pressure, volume, pressure and volume, pressure and volume, ठीक है. इन दोनों के बीच में हम जो ग्राफ बनाएंगे उसको हम बोलेंगे आइसोथर्म. Pressure and volume को बोलेंगे isotherm. Connection between state variable is called equation of state. Real gas may have more complicated equation of state. The thermodynamic state variable are of two kinds: extensive, intensive. Extensive variable indicate the size of the system. Intensive variables such as pressure and temperature do not. To decide which variable is extensive and which intensive, think of a relevant system in equilibrium and imagine that it is divided into two equal parts. The variables that remain unchanged for each part are intensive. जो variables अपन एक system मान लिया, उसको दो पार्ट में डिवाइड कर दिया, ठीक है. जो अनचेंज रहने वाले हैं, जैसे कि उसका टेम्परेचर हो गया, वो तो अपने पास क्या हो जाएंगे, इंटेंसिव. और जो चेंज हो जाएंगे, हाफ हो जाएंगे, वो जाएगा एक्सटेंसिव. इट इज़ सीन इजिली. For example, the internal energy, volume, total mass are extensive variable because they're going to change. Pressure, temperature, density are intensive variable. क्यों? जितना पूरे सिस्टम का है उसको दो पार्ट्स में करो, टेम्परेचर तो उतना ही रहने वाला है. दो पार्ट्स में करो, उसका प्रेशर तो उतना ही रहने वाला है. इट इज़ अ गुड प्रैक्टिस टू चेक द कंसिस्टेंसी ऑफ द थर्मोडायनेमिक इक्वेशन यूजिंग द क्लासिफिकेशन ऑफ वेरिएबल. फॉर एग्जांपल, इन द इक्वेशन डेल्टा क्यू इज इक्वल टू डेल्टा यू प्लस पी डेल्टा वी, क्वांटिटी ऑन बोथ साइड आर एक्सटेंसिव. एक्सटेंसिव यानी कि दोनों के दोनों क्या हो सकती हैं, हाफ हो जाएंगी, पार्ट में चेंज हो जाएंगी दोनों ही वैल्यू, पी डेल्टा वी, डेल्टा क्यू, डेल्टा यू, ठीक है. उसके बाद है थर्मोडायनेमिक प्रोसेस. तो दो तरह की देख ली ना अपन ने, दो तरह के स्टेट वेरिएबल्स होते हैं. ये दोनों स्टेट वेरिएबल्स हैं, पाथ और उससे अलग स्टेट वेरिएबल, एक्सटेंसिव और इंटेंसिव. एक्सटेंसिव कौन से हो जाएंगे, जो चेंज होने के साथ चेंज हो जाएंगे, और इंटेंसिव जो एज इट इज़ रहेंगे, कोई चेंज नहीं होगा, रिमेन अनचेंज. Thermodynamic process, quasi-static process. Consider gas in thermal and mechanical equilibrium with its surrounding. The pressure of the gas in that case equals the external pressure and its temperature is the same as that of surrounding. Suppose that the external pressure is suddenly reduced, lifting the weight of the movable piston in the container. The piston will accelerate outward. During this process, the gas passes through states that are not equilibrium state. The non-equilibrium state do not have well-defined pressure and temperature. In the same way, if a finite temperature difference exists between the gas and its surrounding, there will be a rapid change of heat during which the gas will pass through non-equilibrium states. In due course, the gas will settle to an equilibrium state with well-defined temperature and pressure equal to those of the surrounding. The free expansion of gas in vacuum and a mixture of gas undergoing an explosive chemical reaction mentioned in the section are also example where the system goes through non-equilibrium state. Non-equilibrium state of a system are difficult to deal with. It is therefore convenient to imagine an idealized process in which at every stage the system is in equilibrium state. Such a process is in principle infinitely slow, hence the name quasi-static means nearly static. The system changes its variable P, T, V so slowly that it remains in thermal and mechanical equilibrium with its surrounding throughout. In quasi-static process, at every stage, the difference in the pressure of the system and external pressure is infinite small. The same is true of the temperature difference between the system and its surrounding. To take a gas from the state Pt to another state P dash T dash via a quasi-static process. We change the external pressure by a very small amount, allow the system to equalize its pressure with that of the surrounding, and continue the process infinite slow until the system achieve the pressure P dash. Similarly, to change the temperature, we introduce an infinite small temperature difference between the system and the surrounding reservoir, and by choosing reservoir of progressively different temperature T to T dash, the system achieve the temperature. In a quasi-static process, the temperature of the surrounding reservoir and the external pressure differ only infinitesimally from the temperature and pressure of the system. A quasi-static process is obviously a hypothetical construct. In practice, processes that are sufficiently slow and do not involve accelerated motion of the piston, large temperature gradient, etc., are reasonably approximation to an ideal quasi-static process. We shall from now on deal with quasi-static process only, except when stated otherwise. A process in which the temperature of the system is kept fixed throughout is called isothermal process. The expansion of gas in a metallic cylinder placed in a large reservoir of fixed temperature is an example of isothermal process. In isobaric process, the pressure is constant, while in isochoric process, the volume is constant. So you have to memorize temperature को किस में constant करेंगे isothermal में, और pressure को किस में constant करेंगे हम isobaric में, और volume को हम constant कर देंगे isochoric में. ठीक है. Process is the volume is constant. Finally, if the system is insulated from the surrounding, no heat flow between the system and surrounding, जिसमें कोई heat का flow नहीं होगा, that is known as adiabatic. No heat flow. देखो temperature constant है तो isothermal pressure है तो isobaric, volume है तो isochoric, और heat का कोई flow नहीं है तो adiabatic. सॉरी नीचे भी दिया हुआ है टेबल में. isothermal temperature constant, isobaric pressure, isochoric volume, adiabatic, no heat flow. Isothermal process. For an isothermal process, the ideal gas equation PV is equal to constant. Pressure of given gas of mass of a gas varies inversely at its volume. This is nothing but Boyle's law. Boyle's law is PV is constant, T is fixed. ठीक है. उसके बाद देखो, बस आपको याद रखना है कौन से लॉ में क्या बात बोली गई है. जैसे बॉयल्स है, चार्ल्स है, गेलूस है, क्या, तो सबका पता होना चाहिए किस चीज़ में किसको कांस्टेंट रखा है, क्या वेरिएबल है. ठीक है. आइसोथर्मल के लिए हम यूज़ करेंगे किसको, बॉयल्स लॉ को. ऐसे याद कर लो, उबल गया लेकिन टेम्परेचर वही रहा, बस हो गया याद. बॉयल हो गया बट टेम्परेचर वही रहा. आइसोथर्मल, पीवी इज कांस्टेंट. सपोज एन आइडियल गैस गोज आइसोथर्मली from its initial state to final state at an intermediate state with pressure P and volume change from V to V plus delta V. Delta W is P delta V. Taking and summing the quantity delta W over the entire process, work done आ जाएगा P dV, वॉल्यूम V1 से V2 तक. PV is equal to nRT, वहाँ से P is equal to mu RT dV by V. mu RT log V2 by V1. बस ये हमारी इक्वेशन आ जाएगी. वर्क डन जब भी आइसोथर्मल प्रोसेस में होगा तो वो अपने पास कितना आ जाएगा, म्यू आर टी लोग V2 by V1. नेक्स्ट देखो, where in the second step we have made use of the ideal gas equation PV is equal to mu RT and taking the constant out of the integral. For an ideal gas, internal energy depends only on the temperature, thus there is no change in the internal energy of ideal gas of an isothermal process. The first law of thermodynamics then implies that heat supplied to the gas equals the work done by the gas. Note from equation 12.12 that for V2 greater than V1, W greater than 0, and for V2 less than V1, W is less than 0. That in an isothermal expansion, the gas absorbs heat and does work, while in isothermal compression, work is done on the gas by the environment and heat is released.